Okay, good afternoon. Welcome to Build. My name's Chaz Boyd, and I work on Direct3D. So I'll be talking about graphics here. You can see there's some other 3D experts in the room too. My voice is a little bit odd today because of some apparent festivities that I was at last night. Hope that won't be too much of an issue. It's going to be kind of tight as far as space goes, I'm afraid, but we've got the door closed, so it's time to get started. There was one thing that I wanted to cover a little bit before we get started here, kind of I can't remember the word. Anyway, I want to make sure that people understand how to get the sample apps that we've got. People ask me, well, how do I get all these samples? And so I thought I would just talk about that a little bit. What you do is you go into your device, which your PC, or your laptop, whatever you've got in hand. You go to Internet Explorer, and one of the favorites is the top favorite is your Tailored Web App Hub, or App Web Hub, or whatever it's called. And okay, assuming my network comes through, but that is the link. And when you're on there, you can click on the samples tag like this up here, and then you can search for whichever the samples you want. So simple 3D, D3D, jeez. Or even just 3D I think works. Yeah, so there's stereo, there's the touch samples that we're talking about. 3D Game is one of the ones that I'm going to be showing here in a bit. You can download these now onto your machine and build them during the talk. Just don't get caught. Sorry. Okay, so now we can start with the presentation. The point of this talk is to explain how the Direct3D Graphics API works when you're building a Metro-style application. And most of this talk is going to be in the context of C++. Yesterday we had a talk on gaming in general, and that's something that people need to understand when you're writing. If you write a game like Sudoku or something using XAML, or a Farmville type thing using HTML5, you're still using D3D underneath anyway, so you're getting the benefits of all the performance that we're talking about today. But most of the talk today is going to be focused on the C++ language and API set. Okay. Let's see here. So why would you be interested in 3D graphics at all? Well, the answer is there may be a large number of applications out there. And the ones that use 3D are going to have a lot more customer appeal, a lot more impact, and differentiate themselves from the pack. That's one of the primary reasons to do this. So for an example, I've got an app here. If I can get my device switched over. That's just a very simple app. It's a minor update to one of our samples. And you can see how quickly that came up. This is a 32 megapixel image of the Earth acquired by satellite data. It's wrapped on a sphere. This is a Metro-style app because you can switch to whatever views you want. And this is designed using the scalability performance technologies of Direct3D to enable you to zoom in and out 60 frames a second. I think some of the jerkiness there is due to the resolution of my mouse wheel, not to the resolution of my display. But somewhere down there is Anaheim. We're doing lighting, so you can see that there are parts of the world that are in darkness, nighttime. Anyway, it's just a very simple minor tweak. Now this next application, the one that I was recommending people download and look at, is also something we can look at. This is another three-dimensional application that's actually again. And the interesting thing about this is that it shows off more of what a typical three-dimensional application is going to have. You're going to have, controls, obviously, but we've got an environment, we've got textures on the walls and ceiling, we've got these target objects, we've got a sphere there that's acting as a projectile. There are a variety of elements that are all part of this experience that Direct3D helps you get onto your screen. So we're going to see in this talk, how did those pieces get there? Another example of a three-dimensional application is, beyond the map mashup trick, which is that sort of a startup. Maybe people are doing things like registering on the map all the places where their app first got downloaded or initialized. That's a common trick. Other spaces that involve Direct3D are anybody doing visualization that's coming from, say, data mining of business data. There's a medical scenario right here. There's also the scientific and technical space. People use a lot of 3D. And then, of course, a really common scenario is the game, like I just demonstrated. A lot of you can see all the different elements in there. In this case, we'll go through the mechanisms for how those elements actually got brought up into that 3D scene. So to do that, I'm going to give a little quick overview of the Direct3D object model, really, the structure of the API, enough to be able to understand the samples and what we're doing in this talk and the preceding talk and the subsequent talk. And then a little bit on some of the new functionality that's been added for Windows 8, and in our objective to bring together, tablet and tower. Also, what are additional resources that are available for developers who want to target 3D graphics in their applications, and what are the ways to approach that from an actual getting started point of view. And then the ultimate goal is that by the end of this talk, you'll be pretty familiar with these technologies and easily be able to take one of those existing samples, there's probably around 6 or 7, and modify it to be the type of application that is going to make your customers really happy. Okay, first a little terminology. There's this concept of DirectX, and DirectX has version numbers. The version number that's in Windows 8 is called DirectX 11.1. And it's basically very similar to the DirectX 11 that was shipped in Windows 7. There have been a few minor changes added to it to help it work better inside the operating system. But at the API level, there's just a couple improvements that we've made, mostly to help things work with lower power consumption, and because that's becoming more and more interesting across all possible PC devices. So the overall architecture of the DirectX API, I'm going to show a diagram of how it fits into some of the other components that are in the operating system. One of the key elements of the graphics platform is we have an infrastructure layer called DXGI. And that is what amounts to a memory manager for graphics memory. It also supports things like device control and being able to understand what are the actual graphics chips inside your machine, the adapters and connectors and so on. But fundamentally, it's a resource management system for graphics memory and how you get data into that from system memory and vice versa. And so built on top of that, we effectively have this next layer, which is the first layer that's really commonly used by API developers. And because they're all built on that substrate of DXGI, it means that they can all share resources between each other. So for technical computing, we have the direct compute aspects of Direct3D. In Windows 8, we've added some video functionality now is integrated with Direct3D, and they all share the same underlying data representation and actual memory pool structures, so that you can have something like a video chip decode a video stream into a DXGI region, or memory surface we call it, and then have direct compute perform some calculation on that, and then Direct3D display it wrapped onto a sphere, say. So the plumbing work of making all these pieces interoperate has improved a lot. And then what happens now is we're seeing products built on top of these layers that are targeting more of these specific areas. Direct2D augments Direct3D effectively by adding support for 2D structured graphics, imaging, and text. C++ AMP is a much more language-oriented approach to technical computing based on direct compute. There's a talk on that here, I believe. And then Media Foundation is our higher level framework for AV, video, and audio. And it's also based on the fundamental DirectX, DXGI, and Direct3D, and the lower level video layers as well. And then, part of the work that we've done here enables, because again, these are all based on DXGI, all 6 of these components can share information, and you can transition code within your application between these APIs with pretty minimal pain. And then on top of that, we have the higher level frameworks, application level frameworks, presentation frameworks that are provided as well. And so what that means is that if I have an application that I've written in JavaScript or HTML, and I'd like to have that be performant, you know it will be, because it's based on the DirectX stack that goes all the way down to the GPU silicon underneath. So you may think, oh, I'm just a JavaScript programmer. Well, you're also a GPU programmer now. And so that's really showing how these pieces fit together in terms of your opportunities to make them interoperate efficiently. Okay, so now within Direct3D itself, I just want to give a quick summary of the structure of the API in terms of the objects that it's built from. This isn't down to the metal, very detailed, but it's enough to understand all of the discussions that we're going to be having today and also tomorrow's talk. Fundamentally, it's an interface. It's a boundary between CPU and GPU. It's the mechanism by which CPU code can call into the GPU effectively and have things happen on the graphics side. The way it works is that DXGI fundamentally underneath is used to allocate objects that represent the graphical objects in your application, like the spheres in the scene or the textures on the walls. In this case, this would be a mesh object. There's another type of object, which we call a texture resource, that is used to store the textures that go on the walls of the room. And then there's the final type of object really is what we call a render target, but it's a series of memory regions or surfaces that have been allocated in a way to represent the image that the Direct3D API pipeline will be emitting out onto the screen. And then there is control information on top of that API that's provided as well that governs how the processing happens, that converts my image and my mesh object into a final rendered image. And so the interesting aspect of that is that there are a variety of mechanisms to provide that state to the graphics API, some of which are just structs that you pass in. Others are actual snippets of code called shaders that control the behavior of certain stages of that process that goes from these media resources to a final 3D scene. The D3D device object, drilling in a little bit, is really designed to represent the processing that occurs during creation of a 3D scene, and that's typically referred to as a pipeline because it's a sequence of stages, each one of which does some amount of processing to the media data as it goes through. And what it boils down to is that device object has methods that correspond effectively to the state of that pipeline. And the different state parameters in the pipeline control the behavior of the different stages and control what's going to happen to the data that's flowing through it. Yes. And then, so one of the newer abstractions, this came out in Windows 7, is this concept of a context. And what that is really, it's a view into that device where you have a subset of some of the properties and methods that are available on a separate interface that you can then hand to a separate thread. So it's a mechanism that allows the object to be polymorphic in some sense, in that multiple threads can be accessing the same fundamental graphics hardware, but each with their own copy of, or their own view into that hardware, which is called a context. Okay, a mesh object is basically just a list of numbers that describe the positions of, say, in this case, the corners of that cube. Then there's an index array that goes along with it that tells you what order to interpret those numbers into triangles. It's not a complicated data structure. Our samples use this in quite a few places. But the interesting thing by allocating these objects as resources in DXGI memory, we have the ability to persist that object in graphics memory so that if you're rendering it multiple times, which you usually are trying to do something at 60 frames a second, you don't have to send it anywhere, you don't have to process it. It can stay cached in video memory and be very efficient and low power usage. And it has a header, effectively, that's like an argument declaration that defines the structure of the content so that the API knows what to tell the hardware to interpret that data as. You know, is it float 3? Is it float 16? Different types of formats. Okay, now a texture object is a similar DXGI resource that is representing image data typically. And the way we usually do this in hardware, and there have been several talks, Boris's talk this morning talked about tools that let you treat multi-resolution data like this efficiently in the Visual Studio tools. But the reason that we create, for example, an image and then create all these sub-images of it is that it makes it very, very efficient to zoom that image in real time. When I'm zooming my globe in and out, the hardware is able to select the correct image from among that stack and pick the one one or two that are closest to the right resolution and just average those together to give you a very high quality filtered version of the image that otherwise would take a long time because you would have to be doing a bunch of scaling calculations. So the interesting thing is that you know, it's not a lot of additional memory to store these additional copies because each one's only a quarter the size of the previous one. The total ends up being about 33% more memory to store all those as well. And then again, this has effectively an interface on top of it called a view, which again provides sort of a polymorphism. You can have multiple views onto the same resource that would allow different pixel formats to be stored in the same memory. But this view is what's used as the interface that binds it to the rest of the graphics pipeline. Then the render target object is really the final memory object that we talked about of the three at the bottom of the table. Is basically just raw pixel data. You want it to be pretty much empty when you start because what it's really going to contain is multiple buffers that allow the graphics hardware to be filling up one of them with new imagery while the monitor is scanning out the other or the next downstream component. So we typically call this pair of buffers a swap chain, and it makes it very efficient because you don't have this scenario where the monitor has to wait for the graphics to be done or the graphics have to wait for the monitor to be done. They can effectively collaborate by each having their own copy of the surface. So this swap chain is really one of the fundamental concepts. Now, we'll get into why that's interesting in a bit. But again, like all the other ones, it has a specific view object that you use to declare to the rest of the pipeline what the properties of that are in terms of the format of the pixels. Okay, so now the question is, I've got a Metro style application, and I've created my core window object, and it's got a nice little rectangle of pixels there on the screen that I would like to fill with Direct3D content. How do I get the graphics API and the 3D hardware device to actually render into that little rectangle? And the answer is when you create your application, you'll get a core window which was created for you. And what you do is you go down into the low-level layers of Direct3D and get access to the DXGI layer, which is underlying everything, and you call this new method called create swap chain, and this method is really the one new method that's unique to the Metro style application platform for Direct3D. It's the one way to connect the Metro style application with the traditional Direct3D pipeline. And what happens is when you call that method, it creates a Direct3D swap chain that your current D3D device can render to at however many millions of pixels a second out of your core window. It creates that so that the core window then is able to contain the area that the Direct3D pipeline is feeding its pixels into. So this is really the intersection of the union of those two concepts, the Metro style application and the Direct3D pipeline. And then in most cases, if you're doing a 3D scene, you're also going to allocate a depth stencil buffer, which is used by the 3D pipeline to make sure that the right pixels come out in front of the right pixels. You don't have to worry about what order you draw your scene. For example, if you've got a depth stencil buffer set, that means that the cube will always come out with the front faces ahead of the back faces, for example. And again, it has a view. Now, the rest of the state on the 3D pipeline, I'm going to talk a little bit about the shaders there. The structs that you have, for example, to declare the format of your vertex buffer, the output merger state is a struct that determines how incoming pixels coming from the GPU renderer, the Direct3D pipeline, get combined with the imagery that's already in, say, your core window. Do they just get replace the existing data? Do they kind of take half and half? Do they add themselves on top? There's a variety of options that you can select through that structure. But the more interesting state that's provided to control the behavior of the pipeline is this concept of a shader. And this is really what it boils down to is CPU code for the GPU. And when we design this, we try to make as close as possible to a high-level language like C++ or C# even. But fundamentally, it's squiggly braces and semicolons, and it should be relatively clear to people to how that works. And especially now with the work that the Visual Studio team has done, it's treated inside the IDE like a real language, and you can hit F5 and it will get compiled and integrated into your application and package, and you can load it up at runtime, and all of our samples do this. So it's a very streamlined and convenient approach. This particular shader is the one that's doing, for example, lighting of that sphere globe. What I've done is for every pixel in this entire window, entire sphere anyway, the first thing it does is it looks with that this 110 is a direction vector that I'm basically saying, okay, that's the direction towards my light source. So that's towards the sun, say if I'm the Earth. Then I normalize that because all these calculations work better if all my vectors are unit length. Then what I do is I calculate a brightness or intensity of light at a given point on the surface by taking the dot product between the normal vector of the sphere at that point, which is provided via some structs that are declared further up on the page that's not shown. And I dot product that with the light source direction vector, and that gives me a brightness value. So if the normal to the surface is pointing in the same direction as the sun is, then it's 1.0, and I'm really happy. I get a full, bright scenario. If they're pacing opposite each other, I use that saturate command to clamp it so that it never goes below 0, but at least then I get to 0, and it's basically dark or nighttime at that point. And then the next line of the code is where I sample that stack of, say, those flower textures. The hardware automatically figures out where in that image, including which scale factor of image, to pull the data from and return a color that is the correct color for that point in space. And then I multiply that by the intensity term that I computed in my own code on the previous line to basically say, is it night or day here? So this is a very simple 3-line shader, but it's commonly done, and it's a great way to put lighting on any of your objects in your scene. And lighting is one of those cues that people expect to see from real life, and having that appear in their applications makes things look a lot more realistic as well. Now, there's a little more detail I want to cover here. The VS IDE invokes effectively a command line compiler, which is not the same as the cl.exe that it invokes for C++ code. The FXC compiler that is used for HLSL code is an incredibly highly optimizing compiler. Typically, shaders are not that long, and they run, a typical screen has got 2 million pixels, then each instance of that shader is going to run, 2 million times every 60th of a second. So it's very important to optimize that code. And so we do all that optimization up front during this compile time, and then when it gets brought over to the GPU and actually sent down to the hardware, all the driver has to do is a little bit of optimization to finalize that optimized bytecode into the actual instruction that particular chip computes with. So there's a create pixel shader call, which effectively is how we pass that data into the hardware driver and let it do its own optimization. And because we've done, hopefully, most of the work before that point, the user doesn't experience a glitch or any kind of a slowdown when the actual shader is starting to be used. And the big advantage to this process of doing all the work up front and then just doing the minimal amount at the end is it still allows us to support a variety of instruction sets. So a hardware vendor can just start up a new company who's a hardware vendor. We can have never heard of them before, but if they can write that jitter code that translates to their instruction set, they can run all the DX apps that are out there. So this happens not just so that we can support, say, different vendors, AMD, Intel, NVIDIA, but each of those companies may come out with new generations of silicon that has a more optimized instruction set. Say they have come up with a new way to implement an instruction that takes the place of 5 or 6 other older instructions. They would like to be able to do that in their jitter and then get a speed up like that 5x speed up for everyone. Okay, so that's one of the topics that we're going to cover here today is this whole tablet and tower scenario where we've got a huge installed base of DirectX hardware out there, and there are a variety of different capabilities of that hardware. So what we've done is defined specifications for a sequence of what we call feature levels. Now, these are all targeted through the existing DX11 API interface, which is, at least for a Metro-style application, the one you want to focus on. It's really the only one available in the Metro-style environment. But you can target different feature levels, and we've organized them into a sequence where the functionality exposed at each new feature level is always a superset. So it's not an arbitrary combinatoric scenario where there could just be any feature on any part. You just have to know one number, one integer, and you know the full set of functionality of that chip. And we have a full set of validation tests that we run against all of our hardware to help them align their drivers with the correct feature level for that particular chip. And what this means is that because you're now using the DX11 API, which does support this broader range of hardware feature levels, in many cases you'll be able to use the same code independent of the particular capabilities of the chip. But on the other hand, there will be some cases where for optimal performance you'll want to do something that takes advantage of a higher end feature, maybe out of the 11 functionality level, and then still have another version that works well on the lower functionalities levels or feature levels like the 9 feature level. So it's up to you, and it depends on the algorithm. Some algorithms, like skinning, it doesn't really matter that much. Others, you may want to write an optimal code path for each case, or for some number of cases. Okay, so to continue with this theme of spanning a broad range of silicon, we've actually done some work to update Direct3D 11 in this release. But I wanted to cover some of the more advanced features that were actually shipped in Windows 7 first. And these are the ones that, if you were talking about differentiating, if you want to be able to have an application that really stands out among a large number of other applications, then these are the ones that are going to buy you the big visibility in that sense. So we'll talk about these individually in a bit. On the other hand, we've also got some features that we've added more recently that are specifically focused on optimizing for power consumption. And the reason this is interesting is because at every type of scale of machine, from a tower to a tablet, the power is really one of the gating issues on the performance and the quality of experience you can deliver. Even if I've got a tower machine, it's got a lot of power there, but if I can make my application run with less power, it'll probably run at a higher frame rate, or it'll run cooler and I won't have to pay so much of my air conditioning bill on that issue. And of course, on the low-end devices, power is very important. The other interesting aspect is that a lot of these chips may scale their performance down if they find themselves getting too hot. So it's very important to optimize for power at all scales. So one of the techniques that's at the high-end level we're talking about right now is this concept of tessellation. And what it means is that if I'm running at a very a power-efficient system, I'm trying to use minimal CPU resources, I may not put a large number of polygons on some of my assets. But on the other hand, if I've got a system that's got some of the more DX11 functionality that it's advanced, I don't necessarily have to create a whole new set of assets for my game or my three-dimensional application. I can use the hardware tessellation capability to go in and take the existing asset that I already shipped and improve the quality by subdividing each of those triangles into a smaller number of triangles using a curve patch mechanism. And so this is a fairly popular technique we're seeing today. And it helps, again, with the scaling across a broader range of hardware. we're starting to see people pick up in these applications, certainly in the technical computing space, but also in games and even some of the medical spaces, is this concept of direct compute, which is really designed to be an interface to that same GPU hardware that's used to render 3D scenes, but it's targeted at applications that aren't necessarily graphics. It's really a way to make those ALUs that are inside the graphics pipeline look more like just generic multi-threaded ALUs. And it enables certain algorithms that are of the right level of parallel structure to see some pretty substantial speed ups over even a multi-threaded solution that runs on the CPU. And the other aspect of this is that you can either use the low-level native APIs from Direct3D to do direct compute with the compute shader, or you can use the new C++ AMP syntax, which is effectively a much higher level language that uses this concept of lambdas and then a similar approach to identify the characteristics of code that needs to run on the CPU and the GPU, and then make it much easier to make your application span those both types of processors in the same application. And again, because it's based on the same substrate, I can take my direct computed data and display it pretty much seamlessly because it's all shared out of the same fundamental resource manager. Okay, so there were a few other changes that we made in Direct3D 11.1. One of the ones that's specific to this technical computing scenario that direct compute targets is improved support for some of the double precision algorithms that are common in that space. A lot of the people in the technical computing space really rely on double precision. So we've added a few instructions on those for that purpose. And in addition, for the video people, we added one more instruction to HLSL that helps with image search. So it enables hardware that's got special support for searching in an image to expose that through HLSL. And this can be used either to do things like video compression, where you're doing a motion search algorithm and looking for macro blocks that match, or potentially for doing image recognition, where I've got an arbitrary shape that I'm trying to find within a scene, maybe for like tagging people on Facebook. One of the other interesting features that I did want to talk about, because it's connected to the rest of the story that we're talking about here today, or this week, is this concept of texture compression. Even though I've, in some cases, built my texture image and created all the sub-images of it, what we typically do is compress that data into the format that is really optimal for the GPU to render. And the nice thing about that is it helps in a lot of ways that we're going to talk about today. So there's a range of compression formats that you can select from. We have some tools out there that will let you pick the format that you like. But the big win from this is I'm going to put this in an AppX package that my customer is going to download, potentially over 3G. And so by compressing the assets, we make the package size a lot smaller. They have to pay less potentially in download charges, and more importantly, they don't have to wait as long to experience your application. They don't have to sit there watching some progress bar while your data is coming down. In DX11, we've added support for some new hardware. Recently has come out that supports a couple additional formats that support things like high dynamic range, so you can have 16-bit pixel channel data, and then some higher quality versions of a 4-bit per pixel. But the point is, pick one and use it, and that way your application will be a much smaller AppX file. And you'd think, okay, well, how much does this really buy me? So the texture image that I used in my spinning globe that started out at 32 megapixels, I'm going to go through how that actually turned out. So it's an 8K by 4K image, and I think that boils down to 32 megapixels. And at 24 bits per pixel, 3 bytes per pixel, it boils down to about 98 megabytes of data for just an uncompressed BMP file. So I'm going to say that's the 1x. When I turn it on with BC1 or DXT1 compression scheme, which is what this app actually uses, even though I've generated those MIP maps, which add 33% of memory, because I'm getting a 6x compression ratio out of the BC1 compressor, I still end up with about a 5x memory advantage over what I started with. And that's not really all the story, because when I put my world map file, and you can do this, you can take that application, do the trick that they showed in the keynote of renaming it to be a .zip file, open it up and look at that file inside there and look at the compressed size that zip tells you what it is, and it actually shows that it's only 7 meg. And that's because the encoder that the Apex puts on top of the DXT compressed data adds another, nearly factor of 3 compression ratio to your data. So the net impact on the size of my package that my customer sees when he downloads it over 3G is only 7 megabytes for a 32 megapixel image. And you think, okay, well, how does that compare? Why didn't I just do something like JPEG? And the answer is, well, JPEG would have been a little better, but the problem is the GPUs actually natively speak DDS. They consume, that's their favorite format. It's the most efficient format that a 3D chip can consume. So if I had a JPEG data, I would have to deconvert it back up to probably 100 megabytes and then recompress it back into some other format for the GPU to have efficiently. So it's really just not worth the effort to use JPEG. It costs you about, in this case, a few percent of your size, but it saves you a bunch of work when it comes to getting this into the GPU at load time. Because you also don't want people running your application and having to watch a progress bar once it's running of you loading a bunch of assets and converting them to a different format. And as far as the image quality differences go, the JPEG is a lossy compression scheme. It'll introduce some losses in the image. And the DXT scheme is also a lossy compression scheme. It'll introduce some artifacts. And it's really just a question of you or what type of content you're doing, whether those artifacts are going to be a problem or not, that you can use to decide what level of compression you're going to use. Okay, so when we're doing power optimizations, what we found is a really good way to improve the efficiency in terms of the number of watts consumed is to pay careful attention to the precision of the math that you're using at any point in time. Everybody understands that the power is very important to be efficient with, but the situation right now is that, for example, in Windows 7, all the shaders default, even the pixel shaders that are processing 8-bit color component values, use a 32-bit float to do that. And it's kind of a little bit of overkill. So as of Windows 8, we've added some syntax in HLSL that lets you declare some of those variables as being of lower precision. And that lets the implementation say, hey, the user didn't really need to use 32-bit floats for these. Maybe they can use a 16-bit float. And that may seem, okay, so how is that an advantage? Well, most of these chips, the ones that are efficient, use the same registers to store 32-bit floats and 16-bit floats, but they can store twice as many and then process twice as many. So the performance of my chip for a given number of clock cycles and therefore a given number of watts will double the more for every situation where I can convert that to a 16-bit float instead of a 32-bit float. And in fact, there are even lower precision formats than that some implementations may take advantage of. Another interesting optimization that we've enabled in 11.1 is this concept of a tile-based renderer. Some of the devices out there use this, effectively a cache, that caches part of the image that's being rendered. And so what we recommend is, put a sequence of instructions like this sort of in your code. It's not a lot of work. Those last three lines are really what's important. And then that will enable architectures that have that sort of caching structure to take some additional optimizations that they couldn't otherwise do. So that's just, I'm summarizing the changes that we did to try to focus on these low power scenarios. Okay, so now for the last third of the talk, I'd like to cover really a summary of the full range of developer resources that we're offering you guys to create three-dimensional applications in the Metro style. So the first of the biggest focal point of all these resources is the collaboration we've done with Visual Studio team and developer division. And so they have augmented the Visual Studio product very substantially to support the type of graphics algorithms that we're talking about here. There was a talk on that already this morning that outlined the functionality that it supports, but you can actually do something like, what it's really nice for is you can run your three-dimensional application and find something looks wrong, like that there's a black spot there, or that's the wrong color. And you can click on that pixel and then get back a list of information about all the graphics API calls that were used to contribute to that pixel, and then you can go through those and see which ones were doing the incorrect thing that caused that particular part of your scene to look bad. So it's looking at things not so much from a individual instruction basis, but more of a holistic graphical point of view. It's somewhat analogous to the way these tools like Expression Blend will let you click on a button in XAML or HTML and then blip you to the line of code that corresponds to that button. Here we've got a scenario where I've got some pixel or a tank or an object in the screen. I can click on that and it'll go to the code that caused that to be drawn. Very interesting tool. One of the capabilities that tool also provides is the capability of building all of my .appx package out of the assets that we've talked about here. So we've got 3D meshes, the cube polygon, we've got the texture. All of those need to make sure that those are transferred into the user's machine in an efficient way. And so the Visual Studio process handles that all with the F5 button. And the advantage to this is that the build process is very analogous to the way C++ code works. The advantage to this is, yeah, we want the amount of work that we can do in the tools phase to be as much as possible so that the amount of work that has to happen in the user's experience is the least amount possible. So we optimize our data and we make the package small, don't wait for downloads or uploads. And the way it works is kind of like this. It's very analogous to what happens with C++ code, but everybody understands how that works. So I'm going to run through a couple other asset media types. You can add your own. This is just the way some of our samples are set up. You have an author time asset that somebody's editing potentially inside the IDE or with Notepad. They're editing their shader, like that pixel shader I showed. How do we get that into the package in a very efficient way that the game or other application can load immediately with no progress bar for the user? Well, in the case of shader, we have this fxc.exe tool, which is provided as part of the Windows SDK, and the VS IDE knows where that is and invokes it with a built-in rule on all the shaders that you've got. And then what you get back from that is this concept of a runtime asset, which is the highly optimized piece that we're going to put in the package. And then the Visual Studio uses the packager capability to bail that in with the rest of your content and put it in the Apex file. So in that sense, it's very similar to what happens with C++ code. I have cl.exe that builds my .cpp file and puts it in an OBJ or a .exe, and then that goes in the package. So the same thing happens with HLSL code. That's very clear. But now what about texture data? So the way our samples work is we have a little utility called dxtex, which we use to convert these textures from their raw, for example, the 100 megabyte format into the compressed 7 megabyte, or in this case, 20 megabyte format as part of the build process. And then that goes into the packager and the zip compresses it down. And so it all ends up in the final product in a very efficient way. Now, what about your mesh, your spinning cube? Well, we have a similar process there where there's a utility that's provided as part of each sample, in this case, that converts from some particular mesh format that application expects into an optimized version that goes in the package. So the optimized version is a binary representation of the vertex buffer and index buffer data that will then be consumed very efficiently by the GPU at runtime. And then you can keep going. One of the possible options is to do, for example, an audio sequence that way. You could have an author time format like that's a WAV file, have a little utility that gets invoked as part of a build rule, converts that to an optimized WMA stream that can fit in the package, and then all of these end up being a very small download for everybody. And This is something where people can add more data types, like the next step would probably be an animation sequence, for example. And so the samples that we provided use that kind of philosophy. They all implement that kind of approach to varying levels of sophistication and detail. But I wanted to go through, again, some of the samples that are out there today. The philosophy behind these is to show the structure of a well-written application, to demonstrate kind of the direction that you would want to go on if you're adding 3D graphics to your application, and how to be efficient in terms of the assets that you need, how to make sure that those end up in efficient format and not pay extra space in your package. And I do have this one tip. When you're running any of our samples, there's a dxsample.h file, and if you put that breakpoint there, whenever you have any kind of issue, that'll be the place where you'll be able to find out what happened. So we actually shipped, and these are all on the developer portal, a variety of types of samples. And the first concept is this first ones are as a category is a concept called tutorials, and there's one of those in there for 3D that is a single solution that contains 5 different projects, each of which shows an incremental step in how to set up a 3-dimensional environment for your application. And that's all done in a way that's designed to be very straightforward, so it's not factored into subclasses in an interesting architecture, but it's very straightforward and so easily learned. Now, the next category of sample we call simple samples because most of them have simple in their name somewhere. Simple 3D touch, simple 3D stereo. And these are designed to demonstrate one specific technique at a time. And in that sense, they don't necessarily include all of the functionality that every really proper Metro-style app should have. They don't use the settings or charms or any of those things. And that's just to make it so that it's very clear how to take that one technique and see how it works, and so you could put that technique in some other code base. So you can search for these right now on the portal and download those and start to run those. And then, because when you're talking about a real application, it needs to be more of an end-to-end. We need to show people how all of these different components work together. We do have a couple samples which are a more full and complete implementation. So there's the simple 3D game, which is the one I showed with the orange balls bouncing around, and then there's Marble Maze as well. Those actually do things like show how to integrate audio with the graphics, or become better citizens of the operating system by exploiting more of the functionality that's provided now as part of the APIs for those Metro-style applications. Okay, so in addition to that, we also have downstairs a full lab set up for anybody to come down there and try out these samples, and in specifically cases of these hands-on labs where we'll take you through individual steps, both of how to run and initialize Direct3D, but also how to use the tools that are part of Visual Studio that let you visualize what's happening underneath D3D. That's a very interesting, 709 is a very interesting way to learn about D3D and understand it, because Visual Studio makes you a visual representation of what's going on behind the scenes when you're working with that API. Let's see, what else? Okay, so now this is what you would consider to be potentially a graphics or DirectX focused track, almost. If you go to these talks in this order, or at least watch them on the video in this order, you end up with a pretty consistent understanding of the basics of DirectX and then the high level of capabilities of DirectX by the time you get to the end. It makes a very nice, effectively a whole course on how to learn these APIs and use them. The next one that's tomorrow afternoon, 7:52, is based on this talk, and it provides even more detail about how to do performance optimizations and how to actually get into the details of making your application scale across a variety of different feature levels that are out there. the range of hardware. And that the Tools Talk 761 is a detailed version about the Visual Studio technologies that help support Direct3D, but that already happened this morning, so if you missed it, you'll have to catch it on video. Okay, so the conclusion I'm trying to convey here is that you want to make your application 3D to differentiate it from all the others out there, and fortunately, because of our efforts, Windows 8 is the ideal way to do that. We have all the pieces that you need. So fundamentally, if you're going to differentiate your app, 3D is a really good way to do that. Direct3D is the solution for 3D in Windows 8. The API itself is available both to Windows 8 classic apps and Metro-style apps. And we've got really good support for it in terms of tools and art processing pipelines and so on, so that you should be pretty much unblocked as far as getting started right now. I mean, you can download these things and start them literally right now. And then, you can start building your 3D Metro-style app on the fly. Okay.